Hello everyone, my name is Florian. I work for LINBIT. Those of you who know me will usually expect that I talk about DOBD or high availability. When Baron invited me to come to this conference, I decided to grab the opportunity and talk about something completely different, which is also something that we at LINBIT care about a lot, is block device performance, obviously. And I wanted to take these like 20-25 minutes to examine block device performance or block I/O performance in virtual environments for a little bit. So what are we actually talking about? I would assume that most of you in this room are at this point using some sort of virtualization solution. And those of you who don't, I'm sure have read a bunch of literature and articles about it. And what's interesting about marketing material about virtualization solutions by whatever name, you will usually realize that when they will always compare what overhead that they have compared to just bare metal installations. And the interesting thing is, when you look at those numbers closely, what they talk about mostly is actually just CPU and memory overhead. Now, in fact, for most applications, I mean, short of running a really big number cruncher application or something of that sort, most applications that we find out there are actually not CPU bound, they're I/O bound. So we should really be talking about I/O performance in virtualization environments, because if it's bad, it's likely to bite as much more than CPU or memory memory. So let's take a look at block device performance in virtual settings. So what are we comparing? What am I talking about? I'm talking about relative virtual block device I/O performance in open source hypervisor, aka virtualization environments. And as I'm sure you're aware, when we're talking about block device performance or I/O performance in general, there's actually two things that are quite distinct that are often thrown in one box, but we should really be looking at them separately. One is latency and the other is throughput. And I'm going to give a quick definition of both of these in just a minute. I ran a few benchmarks on the subject for you that I want to share with you, and my reference platform that I used for that was Debian 5.0, Debian Lenny, with 2.6.27 kernel. Now you will correctly say that that's not the newest kernel out there. That's not the most cutting-edge distribution out there, but it's something that enabled me to actually do a very fair performance comparison of all of these things. And what I did was, we will take a look at basically a baseline. Our baseline is going to be just Debian 5.0 chroot install. So we're going to do, my baseline is going to be block device I/O performance in a non-virtual environment. And then I'm going to take a look at Zen 3.2, which is the version of Zen bundled with Lenny, with a pair virtualized guest, with an HVM guest, which Zen sometimes also refers to as full virtualization. It's the stuff that requires Intel VT or AMD SVM processor extensions. I'm going to look at KVM with just straightforward full IDE emulation, and I'm going to look at KVM with pair virtualized block devices as made possible by the VirtIO driver that's been in the Linux kernel, I think, since 2.6.25. Just out of curiosity, can I get a show of hands who of you is currently using Zen in some production environment? Who of you are using KVM? And who's using some other virtualization solutions such as ESX server? Okay, thank you. So, what am I not talking about here? I realize this is the Percona Performance Conference, and you're probably very much interested in absolute performance numbers, so how to get the very most out of your storage and everything. I'm not talking about that right now. So we're not going to be concerned with whether we have a box with like 50 megabytes per second throughput on the block level or 300. And I'm not worried about whether we have 3 milliseconds I/O latency or 100 microseconds. We're just going to take a look at the relative performance relative to a baseline that various virtualization environments entail. I'm not going to talk about non-open source hypervisors, such as ESX server or anything of that nature. I'm not going to talk about network I/O performance. That's also something that you should take into account when you do a real-world performance evaluation. I'm also not going to talk about file system performance, so I'm not going to make any recommendations or whatever about the file systems that you should be using in your virtual environments. And I'm also talking about anything that's non-open source, either in the host or in the guest. Okay, so that's what I'm not going to be talking about. So what is I/O throughput? Well, I/O throughput is actually defined as the answer to the question of how much data can you write to a given device in a given period of time. So in like 1 second of wall clock time, how much data can you actually write to that device? It's actually remarkably hard to do it that way or to measure it that way in Linux. So what we commonly do is we take a sufficiently large chunk of data and then write it and then just measure the time that it takes and then basically just divide that. Measuring block device performance in Linux, or block device throughput, is actually remarkably simple. Anyone can do it. There is a very, very simple and ubiquitous utility that you will find on any Linux box that is really, really nice and handy tool for exactly that purpose, and that is called DD. And DD will simply allow you to write to a raw device or to a file or whatever. And what's nice is that it enables you to use a few options that you can actually gauge your block device performance and not some caching effect or something. So what we do here is we just take a large chunk of zeros, put it in memory, and then flush it as one big thing, right? And the output device would then be the block device in your virtual environment. So the block size in this case, I chose 1 gigabyte, but it's really unimportant. The important thing is that it has to fit in memory, because otherwise your system is going to start paging. And that's going to blow up the entire measurement. And you just write one of these chunks. And what's important here is O-flag direct, which means that the device is actually opened in O-direct mode. So you're bypassing any caches. Because obviously you don't want to measure the throughput of your cache or the measure of your the throughput of your cache and your disk combined, but just this. It's really that simple. You don't need any like real big fancy benchmark tools for that. It's that simple. Measuring I/O throughput is really, really, well, brain dead almost. So let's take a look at this. And there's a few surprising things here. So to the left, the 2 columns to the left are my baseline. And to be fair, so that's basically just that DD running in the chroot of a Debian 5.0 installation. And to be fair, I made the distinction between 2 separate baseline environments, so to speak. One was with a regular 2627 Linux kernel. That's on the extreme left, and then the second from the left is that same thing in the Zen domain 0 kernel, because there are slightly different implications as far as handling of I/O in a Zen domain 0 kernel is concerned. There's actually not much difference here. We're going to see a little bit. We're going to see a bit greater difference when we talk about latency later on. So the overhead that we're getting in para-virtualized Zen hosts is actually remarkably small. So the throughput overhead that we're getting in a para-virtualized Zen environment is about 2% compared to just the bare metal. When we go to KVM with no para-virtualization, that throughput about doubles. That throughput penalty about doubles. So that would be about 5%. But look at what we are seeing here for Zen HVM setups and KVM with VirtIO. The throughput is actually larger or greater than in the baseline system. That makes sense, does it? Well, it turns out that for all of these, we're being lied to. Okay, so depending on how you look at it, it's either the host OS or the guest OS that's actually lying to us. Because what all of these actually do is they keep caching intact on the host level. So you're doing this O-direct thing, which you actually think is going to write directly to the physical device, or the host system thinks so anyway. But in fact, you're not. You're just writing to a cache in the host, right? So the guest thinks it's writing to a disk, whereas the host doesn't really make that disk available. It just has it write to a cache. So the interesting thing is, this is basically all these caches are on by default, which I'm an HA guy, so I care about the protection of my data. I think that's less than prudent, but that's the way that they did it. Now, fortunately, all of these virtualization solutions give us a means of turning that caching off, that double buffering off. Unfortunately, not all of them deliver on that promise. Okay, so KVM and KVM with Vert.io, those are based on reasonably recent versions of QEMU, and QEMU has this nice feature for every block device that you're able to turn the cache off. And when you do that, we're actually now getting reasonable results. So again, we're getting about a 5% throughput penalty here, but when the guest operating system thinks it's writing to the disk, it really is. That means if we get like a hard failure or something, we're actually not losing data. What's worse, however, is that Zen in the HVM configuration, which also uses a modified version of QEMU called QEMU DM, they've apparently not really merged that code change in QEMU yet. So although there is a block tap driver in Zen, which should theoretically force the host to open everything in O-direct mode, and actually there is a variant of that block tap driver that claims to do all sync I/O and not asynchronous I/O as it commonly does. It actually doesn't deliver on that promise. Okay, so it keeps those caches turned on. That's for Zen HVM and Zen 3.2 with Debian Line. As far as KVM is concerned, it actually does the right thing when told to. But overall, as you can see, the throughput penalty that we're getting when we interpret the real numbers, it's not really outrageous. It's bearable. It's not really much of an issue there. So how often are we actually confronted with a situation where we need really good throughput? Well, normally in situations where you're just loading tons and tons and tons and tons of data into your application. Well, would you normally virtualize such an application? Would you put it in a virtual environment? Probably not. So throughput is actually the least of our concerns here. What we should really be looking at is latency, and with latency we're actually getting really surprising things. So what is latency in terms of I/O block device latency? It's basically the answer to the question, how fast can you write the smallest possible chunk of data? Okay? As I'm sure you know, the smallest possible chunk of data that we can write onto a block device in Linux is 512 bytes. That's the hard sector size. The kernel community is currently thinking about making the hard sector size not so hard after all, but as things stand today, we have a hard sector size of 512 bytes. You cannot write to a block device in smaller increments. If you happen to try to write 4 bytes of data onto a block device, what's going to happen is just going to read that whole sector to the disk, then splice those 4 bytes in and write it right back. So the smallest possible chunk of data that we can write to a block device is 512 bytes. So now we want to do a latency benchmark. Remember, we measured throughput with DD. What do we use for a latency benchmark? Well, guess what? DD. So you make a few little changes here to the configuration, and boom, you've got your latency benchmark. What we do here is we use a block size or a chunk size of 512 bytes, which is exactly our sector, and we just fire that at the disk 1,000 times. And DD has this nice feature where it outputs the total time elapsed that it took for these 1,000 writes, which we just did for statistical averaging. Theoretically, we could just do 1, but it's likely we're not getting a really reliable result there. So I'm just doing 1,000 and then dividing that by 1,000. And then, in contrast to throughput, which is measured in megabytes per second, we're just getting an I/O latency, which I can measure in milliseconds or microseconds for that. And then basically we're of course confronted with the exact same issue, namely we're having these virtualization environments, some of which actually do caching when they're not supposed to, and some of them actually keep doing caching even when told to do otherwise. So what's this look like? And now this is really interesting because there's several things that are really interesting here. So one thing is compare the two groups of columns on the very left. That is our baseline in a regular Linux kernel and our baseline in a Zen domain 0 kernel. Now, remember I told you there's specific implications to I/O handling in Zen domain 0 kernels, and that actually translates into fairly significantly increased latency already in the DOM0 kernel, where we're actually not really virtualizing anything at all. Well, technically we are, because the DOM0 is actually virtualized in the hypervisor context. So we're actually seeing an about 18% latency increase there for the DOM0 Zen kernel. But we're actually seeing almost no change on top of that actually in the Zen paravirtualized guest. Okay, so the Zen paravirtualized guest actually has almost no additional latency penalty as compared to just the Zen domain 0. For Zen HVM, well, again, we're being lied to, because here the latencies, the measured latency is actually lower than the baseline, which really can't happen. The same thing is also true for KVM in the VirtIO setting, but when we tell KVM to behave right, namely without double caching, without double buffering, we're actually getting, for KVM with no VirtIO, we're getting 150% I/O latency increase. And that will hurt. That is something that you will actually feel in applications. It is 2.5 times slower than just our baseline in the standard Linux kernel. Remember, this is an exactly identical installation. I'm basically using the exact same Debian installation here. I'm just booting it with different kernels on the exact same hardware. And we're getting 150% latency overhead from using KVM. And now I'm sure you'll understand what the motivation is for supporting the VirtIO drivers in KVM, because they're really hurting in terms of I/O latency. But still, with KVM, with VirtIO, with caches turned off, we get about a 50% performance penalty over the baseline, which is, so 1.5 times slower is better than 2.5 times, but still, it's a pretty hefty latency penalty that you're seeing here from KVM as a virtualization environment. So what do we take away from that? These days, Zen bashing is very much en vogue. You could probably find at least 10 people here at the MySQL and at the Percona conference who will predict that Zen will be dead within a year or 2 years because it's such crappy technology. Well, in terms of performance, it's actually pretty damn good, specifically when we're looking at what should actually concern us the most, which is latency rather than throughput. What we also take away from this is that KVM performance is pretty much sorry with full device emulation. That's kind of expected, because generally all virtualization solutions suffer from that problem. If they don't para-virtualize their block-level I/O to some extent, then they will suffer, because device emulation is just horrendously expensive. When we look at KVM with the VirtIO drivers, then it's doing better, but it's nowhere getting near Zen in a para-virtualized configuration in terms of I/O latency and in terms of throughput, although in throughput the distance isn't as far. And when we're dealing with solutions, with virtualization solutions that use a variant of QEMU for their hardware emulation, then those hosts basically lie to the guests by default. They tell the guests, okay, you've completed this I/O write operation when you haven't, or when they really haven't, because it will then basically go ahead and submit that that I/O operation asynchronously to the bottom of the stack, and so forth. And with Zen 3.2 in an HVM configuration, that is to say, non-para-virtualized, if you're disabling caches in Zen 3.2, well, you really don't. You're not. Okay? That basically concludes my presentation. I'll be happy to take questions. That many? Yes?
I know you said what this session, or what your presentation was not going to cover any non-open source virtualization technologies. But I imagine as in your company, you're actually looking at all the virtualization technologies because it's what's best for your customers?
Our customers tend to approach us when they want open source. So.
Okay, so
but
my question is a leading question.
Yeah.
Have you actually looked at comparative I/O performance on non-open source virtualization software?
I have not, and these slides will be on my blog, which is blogs.linbit.com/Florian. And I encourage anyone sitting in the audience who has the chance to duplicate these on ESX Server, for example, because I'm dying to know. I just happen to not have my hands on testing resources. I have certain expectations, but I'll be very, very curious to find out. So, by the way, did I put my email here somewhere? Ah, I did, yeah. This is our company website, www.linbit.com. The bottom is my blog, blogs.linbit.com/Florian. You will, of course, also find our DRBD community website interesting, which is www.drbd.org, although I wasn't talking about DRBD today. You will reach me by email at florian@linbit.com, and I will hang around for at least a few hours because my flight's not leaving until tomorrow. So if you feel like firing questions my way, please do. I'm here. Thank you.